Ladies and gentlemen, welcome to It's Rainmaking Time. This is Kim Greenhouse. It is my pleasure to have invited Dr. John Medeiros today to discuss what is a new theory and model about color. He is the author of Cone Shape and Color Vision, Unification of Structure and Perception. This is a mind-blowing book and discovery that will alter colorblindness communities around the world, could create inventions to help in the area of perception and vision, but it's so complex that really the one to talk about it is John Medeiros. John, welcome to It's Rainmaking Time.
Thank you, Kim. Delighted to be here.
You studied for many years atomic physics. You had a doctorate in that area from the University of Massachusetts. You've been in research on mechanisms related to laser damage in the retina at the University of Western Ontario. You've been an assistant professor of physics at Penn State University, chief optical engineer with Pacific Sierra Research Corporation. You have huge experience in physics, biophysics, computational science, atomic physics. Why do we need a new theory of color? What is wrong with our existing theory and model for color?
Well, that's a very good way to start in terms of the questions. There is a theory now that actually is fairly widely accepted, and it has been around the essence of the theory has been around for 200 years. And I should mention what that theory is. I mean, the standard theory is that in the retina of the eye, there are three different types of receptors, three different types of cones, and each of them are supposedly having their own sensitivity to different parts of the spectrum, a red cone, a green cone, and a blue cone, if you like. And that as the image is put on the eye, these cones get the different colors, and they are the brain then synthesizes what the colors are by the way these cones are relatively excited. And you know, this theory is widely accepted because it seems so logical and works in a way that people who do photography and other kinds of three-color synthesizing of vision, as it happens in your color monitor and in color photography, for example, works, and it seems like it's plausible. The problem is, and we can get into this later, but there's lots of reasons to believe that there are some serious problems with this model, that it actually doesn't work that way. So where I came from was looking at and trying to understand how the eye worked and how we saw color. There's a couple of things that are rather interesting about these receptors that see color. And most folks know that in the retina of the eye, there are two basic types of receptors, what are called rods and cones. And they're very separate. And the rods are designed for being highly sensitive and operating under very dark conditions, and they provide essentially black and white vision and night vision. And the cones only operate in bright light conditions and provide the color vision. Now, they're named rods and cones for a reason, because in fact, their photosensitive part, the part that detects light, is in fact, in case of rods, rod-shaped, in the case of cones, cone-shaped. And no one's ever explained or even gone into the question of why, in fact, are the color receptors cone-shaped? What's the shape have to do with it? And that is, in fact, the essence of what I'm talking about. It goes, in fact, to the shape. And the shape I'm maintaining is not incidental, but, in fact, actually very critical to how they actually function. And we can get into that. If I may, I'll explain a little bit of how this works in terms of the shape. Now,
maybe you were going to go there anyway, but can you just establish a frame of reference for those of us who are not educated in this realm about how does light get into the eye, or is that too far of a question off in the distance?
No, not at all. I mean, it takes a little visualization. You visualize the eye, and in very general terms, the eye is sort of built like the way people visualize a camera. In the front of the eye is the lens that works to form an image of the outside world on the back of the eye, what's called the retina. And then this retina is a photosensitive layer, and in that retina, there are literally millions of detectors. As I mentioned, these two types, the rods and cones. And the light shines on the retina and enters these receptors. And in terms of the cones, the way to visualize them, in terms of what I'm talking about in terms of this model, you have to visualize that the light enters those cones sort of from the wide end in. They're like light is going into, if you like, a funnel.
Okay.
And that's the key concept. It turns out that the size of these funnels are very, very small. It uses optical fiber effects, essentially, to get in there. And it turns out that, in fact, the size of these cones is actually barely bigger than the size of the wavelength of light itself. That is, light is guided in there and just barely fits in. And that's the key part. That you got to think now about the spectrum of light, the rainbow of colors that we see, that there's different size to light. There's, as you go from the long wavelength end of red to the short wavelength end of blue, white light is a mixture of all of these wavelengths. And if you visualize them entering the cone, what happens is that the cones of our eyes are exactly the right shape and size that as the light enters, as say, for example, if you visualize white light entering the cone, red light, which has the longest wavelength, barely fits in, and it doesn't go very far until, in fact, is shunted out. It actually leaks out the side. As you go further down the cone, light going down there, green light leaks out next. Then at the end, blue light gets all the way down the length of the cone. So the exact size and shape of the cone actually spreads out the spectrum, the rainbow of light, along the length of the cone.
So the existing model says what?
About that, it says nothing. I mean, it says nothing about what the cones do other than the existing model just treats the cones themselves as just sort of a bag of pigment that just catches light, and that, sort of the red cone, what I believe to be the red cones, catches more of the red light. What I believe to be the green cones catches more of the green light. And blue cones catch more of the blue light, and that you try to synthesize what the color is from how those three types of cones are relatively excited. As I mentioned, there are lots of problems with that model, although it's conceptually easy to see how that model might work, that in fact it does not explain a whole lot of different effects about color vision.
Talk about that.
Well, there are a number of effects. If one goes into color vision, there's a whole host of different effects that have been discovered over the years that you have to try to explain. I can mention some of them, but I would like to actually talk about one particular experiment that was done, in fact, over 90 years ago by a guy by the name of Herbert E. Ives, a famous optical physicist back in 1917, did a very simple experiment where he looked at how the eye, in fact, sees yellow light. Now, I should mention, there because of the way the eye works, you can make yellow light in a couple of different ways. For example, you can take just a slice of the spectrum, the pure yellow, and that, of course, looks yellow. Or you can take a mixture of red and green light, as most folks know, and that mixture of red and green light will look yellow. Now, these are called metamers, similar-looking colors made by different parts of the spectrum. So these two yellows look the same. And if you look at them just sitting out there statically, they look the same. And the trick now is, what he did was he actually had a person looking straight ahead and moved a slit of yellow light across the field of view while you're looking straight ahead. So you see the slit of yellow light moving across. Now, if you look at when you look at the slit of yellow light that was made up of this mixture of red and green, what you saw was the front edge of it, the leading edge, was reddish, and the trailing edge of that yellow slit was greenish, with yellow in the middle.